Oh. Oh. All right. So I'm going to read this paper from the 1st of October 1990. And it was published in the Physical Review Letters. It's called Geometry of Quantum Evolution. And I don't want that. Okay, and it's by J. Anandan and Aharonov. I think that's how you say his name. This is the same guy who, with Bohm, they discovered, or they have the Aharonov-Bohm effect. Some people might be familiar with that. Okay, so the reason why I'm reading this paper is because last time I felt like I was trying to make a connection between the wave function, which is a solution of Schrodinger's equation, and I was trying to connect that to like a manifold or something. I don't really know what I was doing. But I think I was trying to connect some sort of geometry thing with the wave function. And then I found, so I was thinking about it a bit more after that video, and I ended up finding a few papers, and I thought, what the heck, why don't I just read papers for myself, and for anybody who watches this, they can also follow along. So let's just get into it. You can see here that this first guy was from Cambridge, University of Cambridge, and Aharonov is from University of South Carolina. The paper was received on the 8th of February 1990. It was published on the 1st of October of the same year. So February, March, April, May, June, July, August, September, October. So that took 9 months from when it was received to when it was published. Alright. Normally I dread reading papers, and I never read a paper from the very beginning to the very end, and I never read every word. Most of the time I'm just scrolling through it like this, and by about the second, third page of a paper I'm usually lost because it's become too nuanced and too specific. So one of the reasons why I want to do this is to force myself to read every word and force myself to sit with the uncomfortable points and try to understand them rather than just skim over it. Okay, so I'm kind of procrastinating getting started because I kind of don't want to do this. But let's just do it. Okay, the abstract. Alright. For an arbitrary quantum evolution, it is shown that the integral of the uncertainty of energy with respect to time is independent of the particular Hamiltonian used to transport the quantum system along a given curve in the projective Hilbert space. Okay. So I'm going to do a lot of dumb, naive things, because I'm dumb and naive. Hilbert space, I have some curve in Hilbert space. And then I'm going from a state over here to a state over here, and independent of the particular Hamiltonian. And then there's lots of Hamiltonians, whatever. Let's just not stop every second and let's just read it. Independent of the particular Hamiltonian to transport the quantum system along a given curve in the projective Hilbert space, whatever. It is the distance along this curve measured by the Fubini study metric. So the Fubini study metric, I've skimmed over this paper, and they tell you what it is, but they don't derive it or give any sort of detail on it. So I'm going to have to supplement this paper with another paper to try to understand this Fubini study metric. This gives a new time energy uncertainty principle. So the traditional one is that the standard deviation of the energy multiplied by this characteristic time greater than or equal to h bar over 2. This is the time energy uncertainty principle. And I've learned a bit about this. And this, just to give some context, delta E squared is defined as the standard deviation in the normal way. So of course these averages are with some state psi, some wave function, and h is the Hamiltonian operator. Now this delta t is not the uncertainty in a time operator. So there is no, from what's normally told, there's no well-defined, I don't really know, but when you learn physics in the standard kind of way, nobody teaches you about a time operator. So maybe there's a definition of a time operator out there, but I haven't learned about it. Oh, exactly, here's that definition for delta E that I wrote above. So delta T is not the uncertainty in some time operator. Instead, it's kind of the time scale of some sort of quantum process. So an example that I think that I can recall is, let's say I have a two-state system, and this could be a two-level atom. So there's a ground state and there's an excited state, and this is my energy. And if let's say I start in the ground state, and then I shine a photon on my atom, this atom will absorb, if the photon is the right frequency, this atom will absorb the energy of the photon and will move into the excited state. And then after some time, delta t later, the photon will be re-emitted. So this delta t is kind of like the characteristic time it takes for the excited state of the atom to decay back to the ground state. And so and this is one specific example of what delta t kind of means. All right, so new geometric mean, but this is the traditional time, energy, uncertainty principle. Oh, and just to give a tiny bit more motivation for it, is the time dependence of a separable wave function goes as like e to the minus I e t over h bar. And what am I trying to say? Yeah, what I'm trying to say. I don't know what I'm trying to say, but what am I trying to say? Oh. Am I trying to say that? Yeah, I don't know where I was going with that. Okay, moving on. So new geometric meanings to time as measured by a clock and the transition probability during a quantum measurement are also obtained. Okay, so we're going to get some sort of geometric meaning to time. Something like that. So it is well known, so that now we're going into sort of the introduction. Good thing this paper is only 4 pages. All right, it is well known that geometric ideas have played an important role in physics. For example, Minkowski's geometric reformulation of special relativity by means of a space-time geometry was very useful in the construction of general relativity by Einstein. But it may be fair to say that there was a lack of the geometric approach to quantum theory until Berry's remarkable discovery that there is a geometric phase in the cyclic evolution of an adiabatically evolving system. So Berry's phase is something that has been talked about a lot around me, like my friends and whatnot, but I've never seriously looked into it, and I think that it's about time that I also look into this Berry phase. This geometric phase was reformulated and generalized to non-adiabatic cyclic evolutions by using the projective Hilbert space, P, which is defined as the set of rays of the Hilbert space, H. It's defined as the set of rays. Okay, so it's some. Okay. The geometric phase factor was obtained as a holonomy. I guess that means it's holomorphic, holonomy, I don't know. The holonomy transformation or parallel transport around a closed curve with respect to the natural connection over P given by the inner product in the Hilbert space. So if I have a closed curve in Hilbert space, I guess I'm transporting this around, something like that. So it's something about going around a closed curve and you acquire a phase. The geometric phase factor, yes, was attained by as the holonomy. What does that word mean? Let's look it up. Holonomy. Holonomy in differential geometry, the holonomy of a connection on a smooth manifold is a general geometrical consequence of the curvature of the connection, measuring the extent to which parallel transport around closed loop fails to preserve the geometrical data being transported. Okay. Now we're going to kind of come into here. In geometry, the notion of connection makes precise the idea of transporting data along a curve or family of curves in a parallel and consistent manner. There are various kinds of connections. Wow, okay. Parallel transport of black arrow on a sphere. Blue and red arrows represent parallel transports in different directions, but ending at the same lower right point. The fact that they end up pointing in different directions is a result of the curvature of the sphere. Oh, I see. So if I transport this way and back here, or this way, I get different directions. All right. Okay. Alright, so the geometric phase, okay, has something to do with, okay, moving some sort of vector around a closed loop. And you do that two different ways toward the same point. You start at a point, you take two vectors, you go opposite direction, or two different directions to another point, and the difference in the angle between these two vectors, it's a difference in phase or something, and that's something to do with the very phase. Okay, so why do we care about all this? Something to do with geometry. Okay. The geometric phase has also been interpreted as an area enclosed by the closed curve with respect to a natural symplectic structure in P. Okay, what does symplectic mean? Actually, let me keep tabs open. Let me open up a tab. Symplectic geometry is a branch of differential geometry and differential topology that studies symplectic manifolds. Okay. Symplectic geometry is symplectic, the study of symplectic manifolds. Great. That is differentiable manifolds equipped with a closed, non-degenerate 2 form. Oh my fucking god. It's going to be one of those nights. Phase portrait. All right, a 2 form, what's it, is that like an area? Okay, fine. It's a differentiable manifold equipped with a closed, non-degenerate 2 form. Oh, fuck, what's a 2 form? 3 form is like dx, dy, dz, so 2 forms like dx, dy. Okay, it's a closed, whatever. Think about some geometry thing. Okay. So I guess I can connect that phase to also this area, maybe. This approach has the advantage that in addition to removing the restriction of adiabatic, wow, there's a lot of crazy words in here, adiabaticity, there is a non-trivial geometric phase even for a closed system for which the Hamiltonian is constant in time. Oy, 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 what is all these words? This approach has the advantage that in addition to removing the restriction of adiabaticity, there is a non-trivial geometric phase, even for a closed system for which the Hamiltonian is constant in time. Unlike in Berry's approach, in which the Hamiltonian must vary with time. Okay, so if we have a constant Hamiltonian, what is non-adiabatic cyclic evolutions? All right, so all of that was kind of dense and difficult to unpack with lots of words that I don't understand and lots of concepts that I need to review. But let's move forward. In this letter, we shall develop a geometric approach towards all quantum evolutions. Not merely cyclic evolutions, okay, I think what they mean by that there is that normally, I'm guessing, but I think normally, you know, the evolution in time is just a factor like this. So it's really just some sort of, it describes some sort of loop in Hilbert space? Hilbert space? All right, so moving on. Yeah. Okay. We assume that a quantum evolution of a state, psi of t, ket psi of t, is governed by the Schrodinger equation. Okay, standard stuff. Where H is the Hamiltonian. Fine. Oh. And yeah, this is standard. Okay. For an isolated system to move in P, it is necessary and sufficient that it is not a stationary state, i.e. it has a non-zero value for the uncertainty delta T in energy defined by blah, blah, blah. Yes, because if this psi is an eigenstate, becomes E psi, and then you just get, this just becomes E squared minus E squared, which is 0. So you can't be in an eigenstate or stationary state of the Hamiltonian if you want to have evolution, I guess. Fine. We shall now consider the most general case when h may depend on time, t, and show that the quantity... I don't like it when they do this, but I don't like it when they give you the quantity and then say, okay, this is my own preference. Maybe some people like that. I don't like seeing something right away where I don't know where it comes from, and then, okay, now I'll show you. But I know that maybe that's like how more math based is they show you the result and then they prove it. But I like to be led along. I like to be led along a little bit because I'm slow. Okay, so we have this quantity here. And this quantity is independent of h. It just depends on the uncertainty in the energy. Let me just read it. Okay, so we shall now consider the most general case when h may depend on t and show that the quantity s equals 2, and then we have to integrate over time of the uncertainty of the energy divided by h bar. And this quantity is independent of the particular h used to transport the state along a given curve C in this projective Hilbert space. Hence, it is a geometric quantity analogous to the geometric phase. So I guess this... Oh my god. So I guess this time is like some path in this Hilbert space, and it does not depend on the Hamiltonian. So that makes it a geometric quantity, I guess. And is in fact the distance along C as measured by the Fubini study metric, which is defined naturally from the inner product in Hilbert space. So this is all very exciting. So the inner product, remember, is, it's stuff like this. So S is some distance along C. Okay, so this is kind of exciting. To prove this, thank you. So we begin by Taylor expanding the ket side t plus dt to second order in dt and use the Schrodinger equation and its time derivative. Okay. So when you Taylor expand this, you get so this is evaluated at dt equals 0, and then this term, right? This term is dt times the derivative of psi over dt, which, plugging in the Schrodinger equation, you get this. Okay. So you could continue this on and on and on, just taking more and more derivatives, but they choose not to. Okay, since h is Hermitian, so is dh over dt of h squared. Then using 2, which is this, I don't know what happened to this dh over dt. Because dh over dt is 0, maybe? Right, so okay, so when I multiply it by this bra, I get 1 by dt over h bar, that. Minus dt squared divided by 2h bar squared. Okay. Minus dt squared for 2h, there's an I, dh over dt Oh, I see. So when I multiply this with a complex conjugate, I'll get 1 times 1, I'll get 1. 1 times 1, I get a minus this, I get a minus. Okay, yeah, I can see that that would work. All right, so we're just neglecting anything to do with dt cubed, we're neglecting, I guess. All right, so the inner product, absolute value squared, between psi and psi of t plus dt. So I'm going from, this state, my Hilbert space, to another state. Is equal to 1 minus dt squared delta e squared over h bar squared. So therefore, this quantity delta e dt over h bar is independent of the phases of psi and psi of t plus dt. And therefore, because it's real, I guess, and therefore it depends only on the points in the Hilbert space, P, to which they project. All right. There are an infinite number of Hamiltonians which we could evolve, which would evolve the state along a given curve C in Hilbert space P. Yes. I think what they mean there is that this left-hand side, you could put any number of values. You could use any number of Hamiltonians that will give you the same delta E. They give you the same distance. Yeah. In general, they give rise to different phase factors for the state vector, but they all give the same value for the dimensionless quantity S, defined by 3. Since S is independent of the particular Hamiltonian used to achieve motion, we expect it to have a geometric meaning analogous to the geometric phase for closed curves in the Hilbert space, P. All right. I think nothing too tricky yet. To investigate the meaning of S, we introduce some geometric concepts. Suppose Hilbert space H has dimension n plus 1, where n is a non-negative integer or infinity. Okay. So it has dimension infinity plus 1. Okay. The unitary group, who the fuck knows what that means, of n plus 1 acting on the Hilbert space. Oh, great. I hate this notation because I have never learned it. Alright, what is the unitary group? The unitary group, in mathematics, the unitary group of degree n, where n can be infinity apparently, denoted U of n, is the group of n by n unitary matrices. Okay. That seems simple enough. Unitary. Unitary just means that if I have some matrix U, this is 1. Or identity. Okay, fine. And my Hilbert space is made from a bunch of, I guess this C is for the complex numbers. And I have n plus 1 complex numbers. Each complex number has 2 real numbers. I think that's how I'm supposed to think about these things. And it can be identified with the set D of orthonormal bases of H, because each element of B can be obtained from a fixed element of B by the action of a unique element of U n plus 1. That's a lot of gobbledygook. Acting on theta. Okay, moving on. On defining an equivalence relation between two orthonormal bases, whenever the first element of both bases is the same, I should be saying bases instead of bases. Bases. Whenever the first element of both bases is the same, the corresponding quotient set of B, which is the same as U of n plus 1 over Un, may be identified with the set of unit vectors of H. It's called the Stifle manifold S sub n. Okay. I'll take your word for it. Okay, so this is the mumbo jumbo that, these are the weeds. Welcome to the weeds. The equivalence relation on S. Okay, so what? Stifle manifold. Oi, man. Okay, unitary. I think I got unitary group. So stifle. There it is. Oh man, Google is so smart. In mathematics, the Stifle manifold is the set of all orthonormal K-frames in math. Okay, somebody forgot to convert that from LaTeX. That's the real number thing, I guess. That is, it is a set of ordered orthonormal K-tuples of vectors in Rn. It is named after, okay, I don't care, it was named after. Maybe I should care. I don't know. Set of orthonormal. Okay, this is too much information. Or maybe it's the right amount of information. Maybe I'm just a stupid one. All right. So the equivalence relation. What is the equivalence relation on Sn? Identifying any two unit vectors related by multiplication by a phase factor gives the quotient set. Who cares? Which can be identified with Hilbert space P was P sub n, i.e. the n-dimensional complex projective space. Okay. I feel like this might be easier than, but it's very overwhelming. Now, U of n plus 1 is a principal fiber bundle over S of n with projection map phi, say, and structure group U of n. Also, S of n sub n is a principal fiber bundle over Hilbert space P with projection map pi, say, and structure group U1, which is sometimes called the Hopf bundle. Also, U n plus 1 may be regarded as a principal fiber bundle over Hilbert space P with projection map pi, phi, or psi, or whatever, I think it's phi, and structure group UN by U1. Okay, so I'm going to be here all night if I try to unpack all of that. I feel like this stuff is probably very important to learn, and I'm not trying to downplay it. I'm just it's just something for me to learn. Probably, I'm just a bit overwhelmed. Okay, so moving on. Let's hope that if I kind of don't understand that, let's hope that I can still get something from this paper. All right, moving on. I'm gonna have to start learning differential geometry, and this kind of notation. I'm gonna have to start getting familiar with it if I want to make progress here. Moving on. There are natural metrics on the above bundles defined as follows. A tangent vector x of un plus 1 is a n plus 1 dimensional Hermitian matrix define the metric h in B by the condition basically the distance between x and y is just 2 times the trace of x times y. So kind of this, what looks to me like an expectation, what you would normally do for an expectation value, kind of looks like. Where x and y are tangent vectors at any point in this orthonormal basis group un plus 1. Okay. Assuming for the present that n is finite, thank you, it is easily verified that this metric is real and positive. Okay, makes sense. I mean, from experience, I think that makes sense. It is and when restricted to the special, I know S is for special, SU n plus 1 subgroup, it is the Cartan killing metric. It's very violent. All right, let G be the metric in S sub n such that phi is a Riemannian submersion. Wow, the person who wrote this is very good at geometry. I.e. d phi is an isometry when restricted to the orthogonal complement of the kernel of d phi. Similarly, define a metric f on the Hilbert space P such that pi is a Riemannian submersion. This f is the Fubini study metric. Okay. What is a Riemannian submersion? Riemannian submersion. In differential geometry, a branch of mathematics, a Riemannian submersion is a submersion from one Riemannian manifold to another that respects the metric's meaning that is protected. Yeah, but what is a submersion? In mathematics, a submersion is a differential map between differential manifolds whose differential is everywhere surjective. Oh, surjective. That looks familiar. Well, at least one element. The notion of immersion. Like an immersion blender. So it's a map. Submersion is a differential map between differential manifolds whose differential is everywhere surjective. So it's some special mapping, okay? Let G be the metric in essence. So that phi is some map. pi some map. Okay. So F is a metric, and it's the Fubini study metric. It's a metric on Hilbert space. That's about as much as I can get from that. All right, there are now natural connections on each of the three bundles defined as follows. Okay. The horizontal space at each point is orthogonal to the fiber at that point. Okay. Let me see if I can understand this. At least now we're using words. So the horizontal space at each point. So if I have some blobby thing, I take a point, horizontal space. So was that like tangent space? I'm guessing maybe. It's like a plane maybe. Is orthogonal to the fiber at that point with respect to the metric in that bundle. Oh, yo, yo, yo. Okay, so what is a fiber? Okay, maybe I have to look for fiber bundle, maybe. Assume it's showing the intersection through the hairbrush is like a fiber bundle in which the base space is a cylinder and the fibers. Okay. Is in the horizontal space is orthogonal to the fiber. Okay, so I think I have some sort of okay, so I think it's something like this. So orthogonal to the fiber. All right, so I think it's something like this. The geometric phase factor, E I beta, is obtained as the parallel transport around a closed curve. Okay, and then if I have some curve on here, there's an e to the I beta. I think we're getting it. Respect the connection Sn. What's my phi? Okay. All right. We now obtain an expression for the Fubini study metric directly in terms of representative state vectors of points B. Interesting. All right, so okay, back to notation I kind of understand. Let psi1 and phi be two arbitrary normalized vectors in our Hilbert space H. Now extend psi1 to an orthonormal basis psi A. such that okay. So I'm guessing A in this example for phi. So psi alpha, sorry. Alpha could be 1, 2, all the way to alpha takes the dimensions of the space. Okay, then phi is just, I take 2 of those. Psi 1, psi 2. Okay, now the curve in B through this basis defined by so okay, so imagine I have some Hilbert space. I won't draw the boundary, but I have these states, I guess, in my Hilbert space. These are like my psi 1, psi 2, and whatever else. And I choose some, I guess, curve through these states. I'm just trying to understand this. And then the distance s goes to e to the is k psi alpha. All right, so I mean, maybe, because if I want to move from one state to the next, right? If I want to move from here to here, I apply a unitary operator onto my state. Maybe. Where the only non-zero elements of k in this basis are psi 2, psi 1, psi 1. Okay. So S is a horizontal geodesic in B, with S being the distance along this curve as measured by the metric h. Okay. Therefore, this curve projects to a geodesic in P with S now being the distance measured by the Fubini study metric f. Clearly, this geodesic, well, I don't think it's very clear, but clearly this geodesic is a closed curve of total length 2 pi. Since phi is equal to e to the isk psi 1. When s is equal to theta, pi times psi 1 and pi times phi are points in P which lie on this geodesic separated by the distance theta. If psi is psi 1 multiplied by an arbitrary phase factor, then psi times the inner product between psi and phi is cos squared 1/2 theta. Alright, I'm confused. Yeah, like this part's not confusing me because I just have psi 1. What does this mean? Since phi is e. Huh. It's confusing me, but let's just keep going. When theta does not equal 0, psi and phi span a two-dimensional subspace C2 of H. The set of rays of C2 is the complex one-dimensional projective space P1 of C, which is also a real two-dimensional sphere. And a submanifold of P, the Fubini study metric when restricted to the sphere is the usual metric on a sphere with unit radius. Every geodesic joining pi is a projection of a horizontal geodesic B, which can be written in the above form by an appropriate choice of basis. Therefore, it must lie on the sphere. If theta does not equal pi, then there are exactly two geodesics joining these two things, which together form a great circle on the sphere. If theta is equal to pi, corresponding to psi and phi being orthogonal, there are infinite number of geodesics with the same length joining these two things, which are opposite points on the sphere. The normalization of our metrics was chosen so that 6 is valid for any geodesic joining these 2 points for arbitrary states psi and phi. Okay, so my questions are, why do we only have psi 1 and psi 2? Why is the curve defined? Why are these the only non-zero elements? So many questions. Well, whatever. I want to get this paper done. Okay, so we therefore conclude that the probability of transition between any two states satisfies 6, where theta is the distance along any geodesic joining pi times psi and pi times phi. Thus, the result of every measurement made on a quantum system in the laboratory has this geometric meaning. Okay, so the probability of finding the state phi in one of these states psi is, I think, just, yeah, it's mapped to this angle theta, which has something to do with the sphere, the unit sphere. In particular, consider the filtering measurements studied by Pancharatnam by sending light through a sequence of polarizers, which provided the first known example of the geometric phase. In such a measurement, a state undergoes a transition. Psi goes to this projection. The new state has a well-defined phase and has undergone a fractional reduction of intensity. Okay, because I think I can work this one out at least. Because originally my intensity was 1, it was normalized. Yeah, and then it becomes this state because this is the identity. So if I insert it, it doesn't do anything. And when I do this, multiply by this complex conjugate, I get this, which is less than 1. Well, less than or equal to. Okay, so I understood something. So the new state has a well-defined phase and has undergone a fractional reduction of the intensity. The phase can be determined by the theorem which states that the new state can be obtained by parallel transporting psi along the shortest geodesic joining pi psi and pi phi in P and multiplying by the non-negative number psi times phi. Interesting. So the new state can be obtained by parallel transporting psi along the shortest geodesic. So this is an interesting point. I don't understand the entire context, but if I just take this out of context, it's a very interesting idea. That okay. But we now also have a geometric interpretation for this number as the cosine half theta. Okay, so I should check out this theorem. Check out that theorem. But this number is related to the distance of this geodesic. Suppose that psi and psi prime equals phi are such that pi times psi and pi times psi prime are separated by an infinitesimal distance. Then, setting ds equal theta in 6, we obtain the following expression for the Fubini study metric G. Okay, so I think I can work this out. So so cosine squared of 1/2 ds, that's squared obviously. So this becomes 1 minus x squared over 4. That's a ds. Okay. So you have 4 sine of 5 squared, the negative sign, 4 equals ds squared. Oh, this is so cool. So this is the distance, and so we're relating this inner product, these wave functions, with coordinates in P. Interesting, interesting, interesting. Equation 7 may be regarded as an alternative definition for the Fubini study metric. Clearly, this definition is valid also for an infinite dimensional Hilbert space, H. A unitary or anti-unitary transformation leaves psi prime invariant and is therefore an isometry in P. Hence, the unitary time evolution 1 and all unitary intermediate symmetries in H are isometries in P. It may be noted that while symmetries such as rotations and Galileibus have a projective representation in Hilbert space H, they always have a faithful representation in Hilbert space P. For example, the rotation of fermion wave functions by 2 pi results in a sign change in H, but the corresponding isometry in P is the identity. From 5 and 7, oh, I see now. So here we've neglected order dt cubed, and if I go back to my Taylor expansion, this is plus order ds4. Aha, interesting. So that's how it works. Okay. So if we relate, we're relating we're neglecting these higher order terms. It would be interesting though if I related. What if we related terms of fourth order? This proves that 3 is the distance along the evolution of the system P as measured by the Fubini study metric for both finite and infinite dimensional Hilbert spaces. Okay, 1 second. I'm going to go get some more water. All right, back. Moving along. In the adiabatic limit considered by Berry, in which psi of t evolves as an eigenstate of h of t, delta E is 0, whereas delta t is infinite, so that ds is finite and non-zero. Hence, this is a degenerate limit, which is not useful in the study of physical manifestations of the Fubini study metric. Also, the above considerations show that even in the adiabatic limit, P is more useful and more geometrical than the parameter space used by Berry, which provides further support to the reformulation of the geometric phase using P. As a simple application of this result, consider a spin 1/2 particle precessing in a homogeneous magnetic field, period. In this case, the Hilbert space is C2, and P is equal to P1 of C is a sphere, and the Fubini study metric defined above is the usual metric on this sphere, corresponding to unit radius. At any instant of time, coordinate axes can be chosen so that the Hamiltonian and the state is then from 2 delta E is equal to mu sine theta. Also from 1, 2 mu dt over h is d phi, which is the infinitesimal angle by which the state is rotated about the instantaneous direction of the magnetic field, and the infinitesimal time dt. Hence, 2 delta E dt over h, which verifies 8. Yes, it is. From 2, yes. This is this delta E, okay. From 1. So in order for it to be a solution to Schrodinger equation, all right, I'll probably continue this in another video.